Thank you so much for the introduction. The aim of my talk is to connect microlocal geometry and derived algebraic geometry to apply it to enumerated geometry and geometric representation theory. Okay, so let me begin with what is microlocal and what is derived. The term microlocal was introduced by Mikio Sato in his study of algebraic analysis, and the meaning is that we work with locally on the cotangent bundle. So in other words, in microlocal geometry, we do not only look at the point of a manifold, but we also look at a direction or co-direction of a given point on the manifold. Okay? And later, Kashiwara and Shapira demonstrated that microlocal viewpoint plays a quite important role in sheaf theory, especially it connects sheaf theory and symplectic geometry using the symplectic structure on the cotangent space. Okay, good. On the other hand, the term derived means it has origin in homological algebra, and the meaning of derived is we work with complexes of vector spaces rather than a single vector space. So for example, derived algebraic geometry is an algebraic geometry based on a complex of algebras, or more precisely, the building block of derived algebraic geometry is a commutative differential graded algebra. Everything in derived geometry appears as a complex of something. For example, the cotangent space in derived algebraic geometry is a complex of vector spaces. Okay, good. So it is natural to ask, can we work with locally on cotangent complexes or its shifts? So what we want to propose is to consider a fusion of this term, which we want to name derived microlocal. Where we work locally on shifted cotangent complexes. Okay. So what we will see is that derived microlocal geometry does not only give a simple replicate of microlocal sheaf theory in derived algebraic geometry, but it gives a new theory, and it has an application in enumerated geometry and geometric representation theory. Okay. So let me explain the motivation of derived algebraic geometry first. Okay. So before giving the definition of derived schemes or derived arcane stack, let me explain the motivation of derived algebraic geometry through Bézou's theorem. Okay, so we are given two algebraic curves in P2 of degree D1 and D2. Okay, the classical Bézou's theorem states that if C1 and C2 meet transversally, then the number of intersection is given by the product of degree. Okay. And it generalizes to the setting when the number of intersection is finite. using the multiplicity of the intersection. If the number of intersection is finite, then the number of intersection with multiplicity is given by d1 times d2, where sharp mult denotes the count with multiplicity. Okay. Okay, but it is not the completely general statement. That is, we can also consider the case when C1 and C2 coincide. The second statement does not cover this case. Okay. The most general statement is given as follows. So we can define the virtual fundamental class, which is a certain homology class of the intersection. And if we integrate the cohomology class 1 against this homology class, we obtain the number d1 times d2. Here, this is a homology class of the intersections called the virtual fundamental class. In some sense, the first statement corresponds to classical algebraic geometry before Grothendieck. And the second statement corresponds to scheme theory. Because the multiplicity depends on the scheme structure of the intersection. And the third statement corresponds to derived algebraic geometry. Because the virtual fundamental class depends on the derived structure of the intersection. Okay, great. Okay. So, yeah. Now, the study of the derived structure is motivated. So let me explain what is the derived scheme. Derived scheme is given by a pair of topological space topological space X and a sheaf of commutative differential graded algebras. Or more precisely, this is a sheaf in the infinity categorical sense. A commutative differential graded algebra is given by a complex equipped with an algebra structure which is compatible with the differential and grading. Okay. And what is important is we have an embedding from the category of schemes to the infinity category of derived schemes. And further, it has a right adjoint. The right adjoint functor is called classical truncation functor, and it is given by the same underlying topological space, and the sheaf of commutative algebra is given by the zeroth cohomology of the sheaf of the commutative differential graded algebra. Okay. So what is important here is that the derived structure is kind of a higher version of non-reducedness. That is, the underlying spaces are same. The only difference is the functions on them. So we should not be afraid of derived structure. Okay. And there is a notion of derived RT stack, and it is defined in the same manner.
What is the first map from scheme to derived scheme? Which structure do you remember?
Yeah, this is a simple inclusion functor. That is, sheaf of commutative algebra defines a sheaf of commutative differential graded algebra, which is concentrated in degree 0. So yeah, this is a simple inclusion functor. Okay. So derived RT stack is defined in the same manner. And it behaves similarly to the case of derived schemes. That is, we have an inclusion from the category of RT stacks to the infinity category of derived RT stacks. And we also have classical truncation functor. Okay, so yeah. And as I explained in the introduction, everything in derived algebraic geometry appears as a complex. So now let me introduce the cotangent complex, which is a complex version of the cotangent sheaf. Let's derived RT stack. There exists a canonically defined complex L of x in the quasi-coherent derived category of x, which is called cotangent complex.
Gradé dans les négatifs degrés.
So yeah, so in the definition of the derived scheme, we assume that the sheaf of algebra is concentrated in non-positive degree. Does this answer your question?
Perhaps it's good to have an example.
Sorry?
Perhaps it's good to have an example.
Example. I will give an example later. Yeah. Okay. So there exists a canonically defined object in the quasi-coherent derived category called cotangent complex, and it upgrades the cotangent sheaf in the following sense. If we take the zeroth cohomology of the cotangent complex restrict to the classical truncation of x, then we recover the cotangent sheaf on the classical truncation. Okay, so yeah, we have defined the potential complex, and so we have a relative version of the potential complex. For a model between diagonal impact, we define the relative potential complex to be the cone of the canonically defined map between potential complexes. Yeah. Okay, so now let me give an example, the most important example of a derived scheme. Okay. We take a smooth algebraic variety U, and we consider a vector bundle over U. And we take a section S of this vector bundle. Then we define the derived zero locus to be the relative spectrum of the Cauchy complex. So, since the zeroth cohomology of this complex is given by the structure sheaf of the structure sheaf of the zero locus of S, we see that the classical truncation of the derived zero locus is given by the scheme theoretic zero locus of S. Okay. And in this case, we can explicitly compute the cotangent complex at a point P in Vs. The cotangent complex at this point is given by the two-term complex concentrated in degree -1 and degree 0. And the differential is given by the dual of the differential of S. Okay. Okay. So now we introduce the notion of quasi-smoothness, or derived version of LCI singularity. A derived impact is called quasi-smooth or derived LCI if X is smooth locally written as derived zero locus. Yeah. The quasi-smoothness of derived impact is very important for any relative geometry. So, for example, most moduli spaces where we study enumerative geometry, like moduli space of stable maps, is quasi-smooth. And this property is needed in order to define certain invariants counting objects parameterized parameterized by the moduli space. Okay.
So here, the quasi-smoothness, what kind of, you use cohomology or that?
This is smooth locally, I mean, locally in the smooth topology.
So the vector bundle is in a classical smooth stack. Like you don't allow cotangent in more than degree 1.
So you mean, do you agree? So am I assuming, how can I say, one artiness or something like that?
Yeah.
So we do not assume one artiness.
So the
here,
vector bundle could be on like a smooth stack, which is like.
So you mean vector bundle or perfect complexes? So are you asking the total space of perfect complexes? Yeah. So if you consider perfect complexes concentrated in degree -1 to infinity, then the total space is quasi-smooth. Yeah. Okay. Okay, so for later application, let me write. Okay, so yeah, as I explained before, quasi-smoothness is important in defining enumerable invariants. So I want to explain in what sense this is useful for defining invariants. Okay, so for a quasi-smooth derived Artin stack, X, one can define the virtual fundamental class, which is an element of the volume of homology of degree 2 times the virtual dimension of X. This is called the virtual fundamental class. And this appeared in the most general form of Bayes' theorem. And this satisfies the following property. If you restrict the virtual fundamental class to the local model, then it is given by the localized Euler class. So the virtual fundamental class can be regarded as a grouping of the localized Euler class. Okay? Yeah, and this is defined by Bayes' advantage. And for later application, let me introduce a relative version of the virtual fundamental class. If we are given a quasi-smooth morphism, here the quasi-smoothness of the morphism is equivalent to say each derived fiber is quasi-smooth. derived fiber is canonical derived enhancement of the fiber with the map. Yeah? Okay. And for morphism, for quasi-smooth morphism, we have a family version of the virtual fundamental class, which is defined as we can define a canonical map from the constant sheaf on X shifted by 2 times the virtual dimension of F to F upper click of the constant sheaf on Y. Which we call the virtual pullback. Okay. By taking the compactly supported cohomology and taking the dual, it induces a morphism between volume homology. Yeah, okay. So why is a point? So this map is given by the virtual fundamental class of X. Okay. Right. So yeah, we have introduced basic concepts in derived algebraic geometry. So now we can explain the microlocal geometry in derived setting. Is there any questions so far?
In this setting, the Fourier homology is the same as the Fourier homology of the underlying.
Right, exactly, yeah. Yeah, I should have explained it, yeah. Here, the volume homology is defined as the volume homology of the underlying space.
So is it just upper street, lower star?
Yeah. This one is equal to the volume homology of the classical truncation. So from now, everything which only depends on the état sheaf or analytic, so état topology or analytic topology on X, like the category of power sheaf or category of contactable sheaves, is defined as the category of these sheaves on the classical truncation. So this sheaf theoretic invariance does not depend on the derived structure.
They probably assume the smoothness in this formula, right? Otherwise, it's not just Qx or Qy.
Smoothness of so when f is smooth.
No, so you wrote Qx and Qy.
Yeah.
But if you want to get more homology, you need this the dualizing.
Yeah. So we have this morphism. Then if you dualize this map, you obtain f upper star of the volume f upper star of the dualizing complex to the dualizing complex, and then you take the hypercohomology. Okay. So then you obtain this map.
Oh, okay.
Yeah. Okay, so now we will introduce microlocal operations in derived setting, which recovers the Butler fundamental, so which gives a new construction of the Butler fundamental class, and also it gives some new invariant. Okay. Okay, so before introducing microlocal operations, we need some preparations. From now, we will assume that all derived arcing stack has perfect cotangent complex. We assume as X is perfect of X. This assumption is not quite restrictive when you consider elementary invariants. For example, moduli stack of sheaves has perfect cotangent complex. But this condition is not consistent with good notion of singularity in birational geometry. For example, KLT and some other singularity does not imply perfectness. So this notion, this assumption might be too restrictive for birational geometry. Yeah, but for applications, so yeah, this is not quite restrictive. Okay. V let DC of X denotes the constructible derived category with two coefficients. Yeah, so this is defined as the constructible derived category of the classical truncation. Okay. And for morphism S from X to Y, we let the conormal bundle of this morphism to be the total space of the -1 shifted cotangent complex. So when F is a regular closed immersion, this recovers the classical notion of cotangent bundle. And yeah, in the derived geometric context, we can define the cotangent, the conormal space for arbitrary morphisms between derived arcing stacks. So this is the reason why microlocal sheaf theory has a very strong generalization in derived algebraic geometry. Okay. And we have zero section morphism. We have a zero section map from X to the conormal bundle. And we have a projection from here to here. Okay, this is not a closed immersion in general, because it can be a stacky vector bundle. Yeah. Anyway, we have this morphism such that the composition of pi and 0 is an identity map of X. Okay. Yeah, perfect. So now we can introduce the derived version of microlocal operation, which is one of our main theorem. There exists a factor from the constructible derived category of Y to the constructible derived category of X, which we call microlocalization factor. Which is defined for regular closed immersion by Kashiwara-Shapira, and it is a generalization of the microlocalization factor from regular closed immersion to arbitrary morphism in derived arcing stacks. And it satisfies the following property. We let D2 be the vector dimension of F. Then the microlocalization factor preserves the perverse T structure up to some shift. Okay. And this is very self-real. Sorry, this is not a factor from y to x. This is the factor from y to the cohomological bundle. Okay. So this is a perverse T exact factor from the constructively derived category on Y to the constructively derived category on the cohomological bundle. And
So there's no assumption on F.
right, so we only assume that X and Y has perfect cotangent complex. This is only our assumption.
So that, what are examples? So would it be something like locally complete intersection?
Right, yeah. So in the classical algebraic geometry, this condition corresponds to locally complete intersection. Yeah.
You don't need like one Artiness of the morphism.
Actually, we don't need one Artiness, so
You can just like
it can be higher Artin stacks.
Yeah, I think of this as the process as like so there is some derived version of the deformation to normal cone,
Right.
which connects these two.
Yeah, that's true. Yeah, and this is representable for arbitrary morphism between derived Artin stacks with this condition. Yeah, and okay. So this is perverse T exact and the Verdier self-real. And also, we can say that it interpolates the upper star functor and upper Schritt functor in the following sense. If we apply a push forward of the microlocalization, which is by abstract nonsense equivalent to 0 upper star of the microlocalization, then this is isomorphic to F upper Schritt. And the pi over Schritt of the microlocalization is isomorphic to 0 upper Schritt of the microlocalization. And this is isomorphic to F upper star of 2 times the factor dimension of F. So this means that the microlocalization functor generalizes both the upper star functor and upper Schritt functor. And also this is very real. So this is a kind of middle version of upper star and upper Schritt functor. Right. So this is our microlocal functor. And this functor has applications in defining enumerative invariants. Okay. So now let me explain how to recover the virtual fundamental class from this construction. Assume now that f is quasi-smooth.
Maybe an easy case if I have just a product and a projection, and I start with the IC of some subvariety on Y, where this is sent when I do
So you consider x times y to y.
Right, yes.
Yeah, so in this case, so this is the box product of the original complex and the Donaldson-Thomas power sheaf on the cohomological bundle, which I will explain later. So yeah, it commutes with taking direct product. It commutes with external tensor product. So yeah, computation of the microlocalization along the projection is equivalent to compute the microlocalization of the constant sheaf. The constant amount. And I will explain what's the answer in this case. Okay. Now assume that f is quasi-smooth. Which is equivalent to say the projection from the cohomological bundle to the base is defined and representable. Okay. Then we have the following theorem. Okay, so we consider the following diagram. By abstract nonsense of the functor formalism, we have a natural map from the pi lower shriek to pi lower star.
Can you say what this means, affine representable?
What this means? Sorry.
What does it mean, affine representable?
So in general, this can be Stucky, so relative stacks, but this is represented by scheme, I should say. So maybe I should say represented by affine scheme, or represented by affine representable morphism.
Okay.
Yeah. So by abstract nonsense, or actually, by using the separate length of this morphism, we have a natural map from pi over shriek to pi push. So here we use quasi-smoothness. Okay. And by the formula here, pi over shriek of the microlocalization is isomorphic to the constant sheaf up to shift. And this one is isomorphic to f upper shriek of the constant sheaf. And we have the Vasserot product here. And one can show that this diagram is mixed. Okay. So this means that it gives a new construction of the Vasserot product using the microlocalization functor. Yeah. So if f is not quasi-smooth, we do not have the morphism from pi over shriek to pi push in general. So we cannot define the Vasserot product for non-quasi-smooth morphism. But by defining this argument a little bit more, we can say something about non-quasi-smooth morphism, which I don't explain here. But I want to mention that in the general case, it should correspond to the DT4 Vasserot cycle on the -2 shift potential of the source. Yeah. Is there any questions so far? Okay. So in the final section, I want to explain the relation between the microlocal operations and category 5 Donaldson Thomas theory. Okay. So let me briefly explain what is the Donaldson Thomas partnership. This is a partnership introduced by Joyce and his collaborators, which categorifies the Donaldson Thomas invariants counting coherent shifts on Calabi-Yau reports. Okay. And the input data to define this object is -1 shift symplectic derived outing stack. So I don't explain the definition of the shift symplectic structure here, but let me give 2 examples, which will be important later.
That's a good question. So in the previous theorem, you have to assume F is quasi-smooth.
Right.
So meaning that you cannot use this to do like DT4.
Yeah, so I mean, so what I want to say is, like, so can I say, when F is not, F is, for example, quasi-smooth, assume that F is quasi-smooth is the next version of quasi-smooth, so it is, the contingent complex is concentrated in -2 to infinity. Then one can show that it seems that the generalization of this procedure implies the DT4 virtual pullback for the -2 shifted cohomological bundle. So it does not recover the DT4 invariance of the DT4 virtual cycle of the original space, but it seems to recover the DT4 virtual cycle of the -2 shifted cohomological.
You also can give a categorification of it.
I don't know whether it has a category. I don't know any categorification of microlocal operation, so I don't know whether it can say anything about category 5 DT4 virtual structure shift or something. Yeah, so, right. So now the input data is -1 shift symplectic derived outing stack. So let me give 2 examples. The simplest example is the absolute cohomological bundle of the constant sheaf, where Z is a quasi-smooth derived one-outing stack. I want to say this is derived one-outing stack. Okay, and another important example, maybe the following example is most important, is if you are given Calabi-Yau threefold, then you can consider the moduli space of compactly supported coherent shifts on the original Calabi-Yau threefold. And this is compactly supported. Okay, these are important examples. And you also need some additional technical data called orientation. I don't explain the definition of orientation because the dependence of the DT power sheaf on the orientation is quite mild. And in my talk, we always have a canonical choice of orientation. So you can forget about the orientation. Okay? So if we are given -1 substitution bracket derived out instance x with a choice of some technical data, then you can define a power sheaf on x or its classical truncation. If you take x to be the modular stack of compactly supported coherent sheaves on Calabian threefolds, then this power sheaf categorifies the Donaldson-Thomas invariants counting coherent sheaves on Calabian threefolds Y. Okay, great. So now let me explain the relation between our microlocal operation and the Donaldson-Thomas power sheaf. So take a quasi-smooth derived one of instant Y. And we let B denote the partial dimension of the Y. Then the Donaldson-Thomas power sheaf on the absolute conormal bundle is given by the microlocalization of the constant sheaf along the constant number up to some shift. So this is a derived or -1 shifted version of the connection between symplectic geometry and microlocal geometry. And we also have a Nadal-Vasserot type equivalence, which I will explain now. Okay, so by the formal property of the microlocalization, this implies that the hypercohomology of the Donaldson-Thomas power sheaf on the absolute conormal bundle is given by the volume homology of the base up to some shift. Yeah, this is an analog of Nadal-Vasserot equivalence on the between the Fukai category on the cotangent bundle and the constructible derived category of the base. Because sorry, this is fine. Because the left-hand side is a symplectic invariant on the shifted cotangent space, and the right-hand side is the invariant on the base. So Nadal-Vasserot type equivalence describes the invariant on the cotangent space or shifted cotangent space by the language of the base. So we can regard this as some analog of the Nadal-Vasserot type equivalence. Okay. So yeah, we have the following corollary. Okay. we take a smooth algebraic surface. And we let Y to be the total space of the canonical bundle of S. And in this case, we can show that the moduli stack of compactly supported coherent sheaves of Y is equivalent to the absolute conormal bundle of the moduli stack of coherent sheaves on S. So this is very easy. And as a consequence of the previous theorem, one sees that the Donaldson-Thomas-Papa sheaf for the moduli stack of coherent sheaves on Calabian threefold is given by the microlocalization. Okay. The difficulty of the study of the Donaldson-Thomas-Papa sheaf in general comes from its construction. That is, it is defined by grouping locally defined Papa sheaves. So it's very difficult to give a global control of this Papa sheaf. But thanks to this corollary, we have a global control of the Donaldson-Thomas-Papa sheaf for the moduli space of sheaves on Calabian threefold of this type. So it can be used to prove a conjecture in cohomological Donaldson-Thomas theory for this Calabian threefold. Okay, let me very briefly explain what is the application. Okay. Let Y be a Calabian threefold. Which we do not assume to be this form. So this is a general Calabian threefold. Then, okay, consider the following diagram. This one is the moduli stack of short exact sequences. And at the level of object, this diagram is given by as follows. Okay. And one can show that Q is proper. Okay, it is conjectured by Ontavik Soiberban, Joyce, and many people. And I think there are several other people's contribution to this conjecture. But the statement of the conjecture is that we can define a natural map from C upper star of the Donaldson-Thomas-Papa sheaf up to some shift Q upper shriek of the Donaldson-Thomas-Papa sheaf. Which induces an associative algebra structure called 3D whole algebra or 3D cohomological whole algebra on the hypercohomology of the Donaldson-Thomas-Papa sheaf. So since Q is proper, by taking the hypercohomology of this morphism, it induces multiplication on the hypercohomology of the dt power sheaf, and it is expected that this has associativity and defines an algebra structure which will be useful in the study of Jonathon-Thomas invariants, and it connects Jonathon-Thomas theory and representation theory. Okay. Okay, so what I have proved with Adeel Khan is this can be proved for local processes. Okay. The conjecture holds for the total space of canonical bundle. At the final I want to mention that this algebra coincides with Kapranov-Vasserot cohomological algebra, and so it coincides with. So what we constructed is a morphism from here to here. And this is isomorphic to the variable homology. Of MS. And it is given by the quasi-smooth pullback and proper push forward. This is 3D hold. And this is 2D hold product introduced by Kapranov Vasserot. So the main point of our construction is that we can construct this map at the level of sheaves on Calabrian threefolds. So yeah, it has some applications on the structure of the 2D cohomological fold algebras, and also it has an application. It is expected to have an application of the wall crossing formula for the Jonathon-Thomas invariants for local surfaces. Okay, that's all for my talk. Thank you so much for listening.